Okay, we'll continue with laying out the elements of our linear elliptic differential equation in one dimension. Okay, let's look at our differential equation again. So we've written it in the form d sigma dx plus f function of x, as we discussed, is equal to 0 in 0, L. Right. Well, one thing you note, of course, is that I'm using total derivatives here. I'm not using partial derivatives. That's because when we are doing doing things in one dimension, we don't even have time. There are no other variables, right? So we're free to do this. Of course, when we go into multi-dimensional problems, we will have to use proper partial derivatives, right? So though I've been calling it a partial differential equation sometimes and a differential equation, really they're one and the same thing for this one-dimensional problem in a single variable. Okay? Just a few more things I need to state here. One thing you will note is that I've been careful to say that we have an open interval over which the differential equation is specified. Okay? So that is an open interval. Right? And you recall what this means. It says that we are interested in looking at this differential equation over the range 0 to L, right? So we have our domain here, that is 0, that is L. This is the domain over which we are interested in looking at this differential equation. But importantly, we're saying that the differential equation does not apply at the points x equals 0 and x equals L, right? So open interval, remember that this implies the domain between x equals 0 and x equals L, but importantly excluding the endpoints x equals 0 and x equals L themselves, right? This is important. And what I want you to do is think of why that may be. Why is it that we specify the differential equation, the partial differential equation, or just the differential equation in this case, excluding the points 0 and L? And to help you think about the answer, recall that we do need to know something about 0 and L. If we don't have the differential equation specified at those points, we must have something else, right? Well, you probably get the answer. The answer is that we do already have boundary conditions specified at x equals 0 and x equals L. If we were to insist that the differential equation also held at the boundary points, we would actually have an over-constrained system. Okay, and this will often manifest itself in the mathematical or numerical solution of problems where you, by essentially developing instabilities in your solution method or situations where you just can't find a solution. Okay, so let me just state that. This is because we have boundary conditions right? And those boundary conditions are either on the primal field itself or on effectively on u comma x, okay, at the boundary points. Okay, and this is why the partial differential equation is always specified over an open interval. This, by the way, is the case for any differential equation, right? Any partial differential equation is not specified at its boundary points. Likewise, if you had an ordinary differential equation, it would not be specified at the endpoints of the interval of interest. Okay, this is an important thing to note and to recognize that it's not purely a matter of taste. It really means something. Okay, it means something mathematically and physically as well. Okay, that's one thing I wanted to state. The other thing I also want to state is, I also want to talk about is the constitutive relations, right? Constitutive relation. And in this problem, we specify the constitutive relation as being sigma equals E times U comma X. All right. A constitutive relation, as the term suggests, tells us something more about the constitution of the domain of the problem. Okay. In this particular case, we started out with the primal field U, but then we introduced another field, sigma. Okay, and what we're saying is that we know something more about the domain of interest, and in our case, the domain of interest is this one. Sorry, that is our domain of interest, right? We're saying that, sorry, it's not X here, it's 0. That is X. Okay, we're saying we know something more about the domain of this bar over the domain 0 and L by specifying this particular relation. Now, we're trying to set this problem up using elasticity as a canonical physical phenomenon, right? In that context, sigma is the stress. Okay, and let me rewrite it here. Sigma is the stress, and it is related not to the displacement itself, but to the gradient of the displacement, which in this setting of linear or linearized elasticity is the strain. Okay. The strain is sometimes given its own symbol, and sometimes, or I guess pretty often, is denoted by epsilon, which is U comma X. Okay, so in the context of this particular problem that we're looking at, the elasticity problem, we are saying that there is a relation between the stress and this which is this field sigma, and the strain, which is the displacement gradient. Okay, and that relation, as you can see here, is a linear one. Okay, so when we say sigma equals E times U comma X, what we have here is linearized elasticity. Right, and it's obvious why we say it's linear or linearized, because that's a linear relation between the stress and strain. In this setting, E is a physical constant that often gets called the Young's modulus, or you may simply call it the modulus in a one-dimensional setting. Right? In a one-dimensional setting, there is only one modulus. Might as well call it the Young's modulus. Okay, so this is the other bit that I wanted to state about this, the physical phenomenon that we are using for now as a canonical setting for the problem we are considering. The probably very last thing I will do is restate essentially the same problem, but in the context of a different physical phenomenon. Okay? So let me state it here. The 1D scalar, because remember we said that in 1D everything is essentially scalar. So the 1D scalar linear elliptic problem also models heat or diffusive mass transport. Okay, let's suppose we're talking about heat transport. Okay, in that case we would state the problem as following. We would say find u function of x, which is a mapping again from this domain 0, L open interval to the one-dimensional real space. Okay, given, now I will attempt to use different symbols here. Okay, I'm going to use different symbols, but because we're talking of the heat conduction of the heat transport problem, I will also state here that what we're talking about when we talk about U, the primal field, we have the temperature in mind, okay, for heat transport. Okay, so find the temperature U, which is a mapping from 0, L open interval to R1, given the following. Okay, given U0 and UG, or now I want to reserve T for traction. So for the other sort of boundary condition that we could have in the context of heat conduction, I'm going to use J bar. Okay. We're given these. We have our forcing function F and the constitutive relation now. In this case, the constitutive relation that I want to use is going to be for the heat flux, and I want to use a different symbol instead of sigma here. Okay, I'm going to use the symbol J for the heat flux. J equals minus kappa u comma x. Okay, right? Such that we have the following. Okay, minus d dx of j equals f of x in 0, L. Okay, all right. Now let me put down the boundary conditions, and the boundary conditions are u at 0 equals u naught, and either u at L equals ug. Right, now both of these U at 0 being U naught and U at L being UG would be given temperature conditions, right? Or at x equals L, we may also have the condition that J at L, okay, equals minus J bar, okay? Right, so this is how we may specify the heat conduction problem. Now, in doing this, observe that what we have here is to be thought of as the divergence of the heat flux, okay? And in fact, J in this case would be the heat flux. Okay, what I've circled here would be the divergence of the heat flux. Okay, in the context of heat conduction, what we would be saying would be that this would be the negative divergence of the heat flux. Okay, so the minus divergence of the heat flux. What we would be saying is that the negative of the divergence of the heat flux in the context of heat conduction is the amount of heat you're supplying to a particular little volume element in this domain of interest. Okay, I already said that that the conditions on U would be temperature boundary conditions. So let me specify that also. Okay, so the Dirichlet boundary conditions would imply, in this case, temperature boundary conditions, okay? And finally, the Neumann boundary condition would imply a heat flux boundary condition, okay? In particular, this condition that J at L equals minus J bar, okay? This would have the following significance, that J bar, as I've written it here, would be the heat influx at x equals L, okay? So if you look at this problem that we've just described here rather quickly, and you just make substitutions, right? You just make substitutions instead of, instead of J, you go back to sigma. Instead of kappa, you go back to E. And instead of J bar, you go back to T. Okay? You will see that the problems are, in fact, the very same, right? Mathematically, it is exactly the same problem. But we know that this is the problem of steady-state heat transport or diffusive mass transport. Okay, so this is important to note that there is a multitude of problems that are described by the same differential equation, or the same partial differential equation. It's just a matter of redefining our fields of interest, boundary conditions of interest, and giving them ascribing to them different physical interpretations. Okay, and because we are interested in developing in this class finite element methods that apply to a range of problems, we will tend to focus more upon the underlying differential equation of interest, and we will repeatedly make connections with the physical problems, but we will also bear in mind that rather than thinking of the finite element method as a problem to be developed, as a problem applicable only to structural mechanics or only to heat conduction, it really is a lot more general than that. All right? Okay. So this is where we were, and this is where we are going to stop for this segment.